Next, we take a look at the formal definition of continuity, or continuity of a function or a continuous function. So just to remind you of our intuitive definition, we said that a function was continuous if it looks like this. In other words, if it can be drawn without lifting your pencil. So this is continuous. Something that's not continuous might have a hole in it. So this is not continuous. Not continuous. Or it could have a jump in it. This is not continuous. Some examples of functions that are not continuous, the amount of friction acting on an airplane landing gear at the moment it lands. You go from no friction to when it lands, suddenly you have sliding friction and you have a huge amount of friction that's discontinuous. Another example of a discontinuous function could be a shock wave. So when you have a jet engine, so let's say this is the tip of a supersonic aircraft, you have a shock wave. So you can have an oblique shock wave form up front. And what a shock wave is it's a discontinuous jump in pressure, temperature, and density of the ambient air or the atmosphere. So you have one pressure and temperature and density upstream, and then you have a lower pressure, temperature, and density on the other side of the shock. And there are all sorts of thermodynamic relations that will tell you, based on what type of shock you have, the ratio of the pressures, the temperatures, and the densities using various thermodynamic laws. So why do you have this discontinuous jump? Well, a supersonic speed, supersonic, means that you're traveling faster than sound. Now, the way change is propagated through the air is through sound, right? So you can hear something coming. If you're traveling faster than sound, it's impossible to hear something coming. Now, what is hearing? Why is it that you hear certain sounds? Well, it's because of basically changes in the air density. So you have, basically these density or pressure waves in the air that resonate with your eardrum, and you hear that as sound. So if you're traveling faster than sound, those changes in the air density cannot propagate upstream in advance of your vehicle. They can't go faster than your vehicle. So your vehicle is going as fast as information can go upstream. So that basically means that you're not sending a signal through the air ahead of your vehicle. That signal is staying right in the front of your vehicle as you travel through the air. The result of that physically is a sonic boom. People on the ground will hear a sonic boom when a supersonic aircraft flies by. So you basically have this undisturbed airflow ahead of the shock, and then a sharp discontinuous change in the pressure and the temperature and the density. And that sharp sudden change in air pressure is what results in the sonic boom. So when you're on the ground and you hear a sonic boom, it's when the shock wave passes right by you. And you get that sharp discontinuous change in density, and you hear that as a loud, like kind of crashing, thunderous noise. Another example would be the number of popped kernels in a bag of popcorn in your microwave, right? So you don't have this nice gradual change in the number of popcorns. I don't know if that's popcorn things in your bag. Instead, you get pop, right? So you have discontinuous jumps in the number of kernels that have popped. So those are some examples of real-world phenomenon where you have a discontinuous function. So they say, well, what's the big deal? Why can't everything be continuous? Well, there's plenty of things in the real world that are discontinuous like that. Okay, so what is the actual real definition? Well, the real definition, now that we know limits, we can write it a little bit more formally than saying you can draw it without lifting up your pencil, even though intuitively that's a pretty good definition. We say a function f is continuous. And first we just start with continuity at a point. So it's continuous at the point x equals c if, first of all, f of c exists. So in other words, the function actually has to be defined at the point for it to be continuous. And most importantly, if the limit as x approaches c of f of x is equal to f of c. Okay. So something you probably expect to be, you knew in your heart all along. So here's a hole. We'll leave f of c out of this picture for a while, and we have a limit. So the limit has to exist as x approaches c. And in order for the limit to exist, it has to be the same from the left side and the right side. So you have to have the same limit from the left and the right-hand side, which both have to exist. And they have to go to the same limit, let's say L. That's great. Well, then also, f of c has to be defined. So there has to be some output for the input x is equal to c. And the output has to agree with the limit. So you can't have an output up here. That's not continuous, right? Because the limit's down here and the output's up here. So let's get rid of that. The output has to be right where the missing hole would be. It has to fill the hole and connect. So you have a nice bridge. The outputs as you approach it from the left are equal to the outputs as you approach it from the right, and they're equal to the output. That's continuity. And then we say that f is continuous on a, instead of just on a point on an interval, if it's continuous for every point on the interval. So continuity is really something we define at every point. And if you think about it, something can be discontinuous at a single point and continuous everywhere else, right? When you're landing, like right when you touch down, you have a discontinuity, right? So you're nice, continuous, and then poof, discontinuous, right? Not necessarily your height, but maybe the amount of friction. Zero friction and then psh, high amount of friction that continues, right? So you have a discontinuous jump from zero friction to large friction right when you're touching down. Your velocity, even though the position's continuous, your horizontal velocity, it's going down and then discontinuously stops to zero. You don't level off, it's just a jump down to zero velocity. Right. So an important theorem for continuous functions is called the intermediate value theorem. It's one of those theorems that when you read it, it sounds really obvious. So if f is continuous on the interval from a to b, so that's a closed interval on the x-axis, and if k is any number between f of a and f of b, so in other words, k has to be somewhere between the y value at a and the y value at b. So then, before I even write the second half, let me draw a picture. Y, x. So when you read a theorem, if f is continuous on the interval from a to b, let's draw an interval, a to b. A to b. If k is any number between f of a and f of b, well, let's say, okay, maybe the output here is at a is this height, that will be f of a, and maybe the output at b is right here, and we get f of b. So k is any number between f of a and f of b, so k is something like that. So k is any number between the value at the left endpoint and the value at the right endpoint. So then there exists, when you say there exists, it always is implied at least one. Could be more, but you know, it doesn't have to be exactly one. It could be 2 or 3 or 12. There exists at least one point x equals c such that f of c is equal to k. So in other words, this blue stuff in the graph is a given, and what the theorem says, in that situation, pick any k between f of a and f of b, there's going to be a value c somewhere. Maybe it happens to be here, I don't know, but it's going to be somewhere between A and B. Oh, I should say that. There exists a point C in the interval from A to B. So this symbol basically means contained in the set from A to B. So C is somewhere, so in other words, A less than or equal to C, less than or equal to B. There's some number C on the interval such that f of C is equal to K. So some number C between A and B such that f of C gives you that K. Another way of saying that is that if you have a continuous function from A to B, every y value between f of A and f of B has to be hit at least once for some x value, right? So maybe a continuous function looks like this, right? If you don't have any, so on the contrary, if you don't have any outputs equal to k, there has to be some sort of hole in the function, because how do you go from down here, this height, to this height up here without passing through k? Basically, if you have a continuous function, you're going to pass through k at some point. That's all the intermediate value theorem says. Sounds cool. Okay. Well, now let's do something that's a little bit astonishing. This is the famous problem. So suppose a Tibetan monk, I don't know why it has to be a Tibetan monk, but if you want to have a monk in a different country, Adrian monk in San Francisco, that's fine. Tibetan monk leaves his monastery. I don't know how to spell monastery. At 7 o'clock a.m. one morning, and he travels a path up a mountain and reaches the peak at 7 o'clock p.m. I don't know exactly how probable that is with mountain distances and whatnot, but just for the sake, this is the way it's usually stated. So you have a mountain, and there's the monk at 7 p.m. and there's this nice trail, and then here was his monastery where the monk was at 7 a.m. and he travels the nice trail to the top of the mountain. And then the next day he spends the night maybe meditating at the top of the mountain, and then the next day, day 2, he reverses it. Right, so 7 a.m. he's at the top, and then 7 p.m. he's at the bottom. Now, the monk brought his running shoes with him, so, sporadically he was sprinting for a little bit, sitting and resting, sprinting. Sometimes he got confused and went in the wrong direction. Then he went this way, and he went back. Then he went really, really fast because a bear was chasing him. Then he stopped to rest. Eat some trail mix, went back, realized he was going the wrong way. Really sporadic. I mean, just completely chaotic mess of moving forward. Always traveling along the same path, but just, all bets are off with this monk. The next day, same story coming back, just completely sporadic. So the question is, does there exist a point on the path? Don't know where it is. Maybe it's here. But in principle, is there a point that the monk is at that point at the exact same time on both days? So maybe the first day he passes through this point at 9:43 a.m. And then on the second day on his way back, he passes by the same point at the exact same time. Is there a point like that? Does there have to be a point? Obviously there could be, but does there have to be one like that? Interesting problem. Well, let's use the intermediate value theorem to prove that it's true. I guess I do like this picture. We'll scratch it. So, let's start with a graph. So we'll try to figure out, what's going on. So we'll use time, 7 a.m., 7 p.m. And then distance along the trail. So this would be x of t. This is the monk's distance along the trail. It makes sense to put the base at 0. I'll put it up here. So this is the monastery, and this is the top, the peak of the mountain. So he starts at the monastery at 7 a.m. and reaches the peak at 7 p.m. Well, its position is continuous. You can't, unless you're a quantum mechanical particle, you can't just disappear and pop out somewhere else. So you're going to be moving. He's traveling up the hill. He stops for a break. He goes fast. He stops for a break. He goes back a little. Goes forward. Whatever makes some gradual progress. He goes back and forth a little bit. But at 7 p.m., he's at the top of the mountain. Day 1. So that's day 1. Day 2, 7 a.m., he's at the top of the mountain. And then maybe he stays there. Maybe he doesn't even start. He goes really fast. Goes back, and then fast again, slow break, and then he starts getting motivated, very fast, very fast. You see, already, these two paths have to cross, right? There's some point, there's some time that he was at the same location at both ways. And so the way to do is call this maybe R of t. I guess we did call the first one x of t. So this is R of t for the return. The way to do this is to maybe let's say u of t for the first one, up. I know I didn't do up and down, but u of t and r of t, that works. And let x of t equal u of t minus r of t. And there you go. Why does that work? Well, u of t minus r of t, 0 minus the distance, that starts with a negative, and then distance minus 0 is a positive. So at 7 a.m. we have a negative number for x, and at 7 p.m. we have a positive number for x. And it's a continuous function because the difference of two continuous functions is also itself continuous. So you're starting out with a negative, you're ending up at a positive. You have to go through 0 by the intermediate value theorem. There are a few details to write it down nice and neat, but that's the basic idea. So it's a cool problem.